All right, let's dive into one of the most classic coding problems out there, reversing a string. But, we're not just looking for any old solution. We're on the hunt for the optimal one, the one that's super clever and incredibly efficient. Let's get right into it. So just imagine this for a second. You're handed the word hello as an array of characters. Your job? Reverse it. Sounds pretty simple, doesn't it? Well, here's the kicker. You have to do it in place. That means you can't just create a shiny new array and build the reverse string. Nope, you've got to work with what you're given. And that constraint, my friends, is what separates a pretty good solution from a truly great one. The fancy term for it is O1 extra space. All that means is we can only use a tiny, constant amount of extra memory. And it doesn't matter if the string is 5 characters or 5 million. This is really the heart of LeetCode problem 344. Just to be super clear, an in-place algorithm works directly on the input data itself. It just shuffles things around, overwrites characters, and transforms everything right where it is. No making big, new copies. So how in the world do we pull this off? The answer is this absolutely beautiful and widely used technique called the two-pointer method. It's such an elegant way to solve a whole bunch of array and string problems. And honestly, it's perfect for our reversal challenge. So here's the game plan. We set up 2 markers, or pointers. We'll call them left and right. The left pointer kicks things off at the very beginning of the array, index 0, and the right pointer starts at the very end. Think of them as a team, ready to work their way toward the middle.
Okay, theory is great and all, but seeing this thing in action is where it really clicks. So let's trace the logic step by step as we reverse our good friend, the word hello.
So we start with our array. H-E-L-L-O. Our left pointer is sitting on H at index 0, and our right pointer is all the way down at index 4 on the O. Their mission, should they choose to accept it, is simple. Swap the characters they're pointing to. First up, we swap H and O. Bam. The array becomes O-E-L-L-H. Then, both pointers take one step inward. Now left is on E, and right is on the second L. We swap them. And the array is now O-L-L-E-H. The pointers move in one last time, and now they've met, both pointing at that middle L. Our rule to keep going is while left less than right. Well, they're not less than each other anymore, so the condition is false, and our loop stops. And just like that, the string is completely reversed. So we know it works, which is great. But what makes it optimal? Well, it all comes down to its incredible efficiency, both in terms of time and, most importantly, space. You see, if we tried to solve this with something like a stack or a recursion, we'd need extra memory that actually grows with the string's length. That's what we call O of n, or linear space. But our two-pointer method, it's O of 1, constant space, which is exactly what that in-place requirement was all about. And this just says it all, right? O1 space is possible because the only extra memory we ever need is a single temporary variable to hold one character while we're doing the swap. That's it, one variable. It doesn't matter if the string is 5 letters or 5 million. It's amazing. So let's just quickly break down that core logic. The time complexity is O of n. Now, even though we only go through about half the array, the number of steps we take still grows linearly with the size of the string. And that while left less than right condition, that is the brain of the whole operation. It's what stops the pointers from crossing over and undoing all our hard work by reswapping everything back to the way it was. And for strings with an odd length, this condition is also what cleverly makes sure that middle character is left completely alone, exactly where it belongs. A truly great algorithm has to be tough. It needs to handle not just the easy stuff, but all the weird, tricky inputs you could possibly throw at it. We call these edge cases. Let's see how our two-pointer solution holds up under pressure. First up, what if we get an empty string, an empty array of characters? Does our code just crash and burn? Nope, not even close. In this case, left would be 0, and right would be -1. So that condition left less than right is false right from the get-go. The loop never even runs once, and the empty array is returned just as it came. Perfect. Okay, next test. How about a really short, odd-length string? What happens with A, B, C? The algorithm handles this flawlessly. A and C get swapped. Then the left and right pointers both land on the middle element, B. The loop condition becomes false, and B stays right there in the middle. We get CBA, which is exactly what we wanted. Final challenge, what about a palindrome? You know, a word that's the same forwards and backwards, like aber? The algorithm just does its thing. It swaps the first A with the last A and the first B with the second B. But since it's swapping characters that are identical, nothing really changes. The result is the same palindrome, which is the correct reversed version. It passes every single test. So if you take away just one thing today, let it be this. This little phrase perfectly captures the entire soul of the algorithm. 2 pointers, swap the ends, move inward, meet in the middle, and you're done. It's a mental model you can use forever. And that brings us to our final thought. We've seen just how powerful this pattern of converging pointers is for reversal. But this is just the tip of the iceberg. So the question I want to leave you with is this. Where else could you use this idea, starting at the ends and meeting in the middle, to solve other complex problems?